Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're looking at acid-base chemistry, the last concept of review before we start into the first set of new concepts, which would be thermochemistry. Quick review for those who, if these don't make sense, you need help, you can always email me at ltswpd@gmail.com. Also, you can go back to my Chem 1 playlist, days 158 to 170, we talk about acid-base chemistry. Again, remember to like, share, subscribe. This is just so people can see it. I'm not in the illusion that we're going to actually make money here, but this is just for fun. So anyway, we're looking at acid-base, and we're going to make sure I do a quick review on nomenclature. There's three examples there: HCl, H2SO4, and HNO2. Each of those is one of the three different types of acid nomenclature. The first one, HCl, is a binary. Remember, when we do binary, there's no oxygen, just hydrogen and one other element. There might be multiple of them, but there's no oxygens involved. So when we do that, it's hydroic acid. So in the case of HCl, that's chlorine, so it'd be chlor, so it's hydrochloric acid. SO4, that's sulfate. Remember, it's inside the box. O4, inside the box is an 8. So therefore, that's the rule for 8s is ic acid. So it would be sulfic, but they didn't like that too much, so they make it sulfuric acid. And then NO2 is outside the box. Outside the box, O2 are ites. So that's nitrite for ites. Acid, it's us acid. So nitrite, take the ite off, add it to us, nitrous acid. Alrighty, so quick other review here, identifying strong and weak acids or bases. For acids, we're going to just say that if it's binary, it's always strong. That's not always the case. Just make it simple for right now. For polyatomics, take the number of oxygens minus the hydrogens. If that number is greater than or equal to 2, it's strong. Less than 2, it's weak. For bases, we're going to just keep it simple right now. Hydroxides are strong. Doesn't have hydroxide, it's weak. Alrighty, so let's look at the process of dissociation. I've got 6 of them here. The first one we said was a binary. Binaries are always strong. Strong means they dissociate 100%. There's no equilibrium, so it goes direct. Now when we dissociate, we break down into its ions. So therefore we have H plus and Cl minus, the ions that exist inside of there. And everything's balanced up, so that's where we go here. For the second one, for sulfuric acid, H2SO4, that's 4 minus 2, that's 2, which is equal then to 2, so it's strong, so it's also direct. No equilibrium there, going one way only, all of it going to product. Again, we're dissociating to its ions, H plus and SO4, 2 minus. We're going to start making 2 minus instead of minus 2. That's not balanced though, because we have 2 hydrogens here and 1 here. We don't make it diatomic because it's not an element, it's an ion, so it's 2H plus. And the third there is a base. We consider that a strong base because hydroxide. So again, it's direct, 100%, not equilibrium. Break into its ions, Al3 plus OH. Again, it's not balanced because I have 3 here and 1 here. So I put a 3 in front of there. Now for the first one, nitrous acid, HNO2, that's 2 minus 1, 2 oxygens, 1 hydrogen, that's 1. That's not greater than or equal to 2. So therefore it's going to be equilibrium. When it forms up, we're going to go into its ions though still, H plus and NO2, and we're going to do what's called a equilibrium product constant. The KEQs we talked about before in Chem 1, we're going to call it KC and KP in Chem 2. All right, for the second one, H3PO4, remember that name would be ic acid, so that would be phosphoric acid. 4 minus 3 is 1, so therefore it's also equilibrium. It's going to come forward and back. We're going to have reactants and products dissociating into its ions, H plus and PO4, 3 minus. Again, that's not balanced. We put a 3 in front of it. And then, because it's not hydroxide for the base, that's a weak base. Equilibrium, Ag and CO2. It's not, silvers aren't balanced. We're going to put a 2 in front of it there. So that's our dissociation process. Now, the next thing we'll look at is pH. Now, remember we talked about pH. pH is the measure of acidity. pOH is the measure of alkalinity. We have 5 equations here. pH is equal to negative log of hydrogen ion, POH is negative log of hydroxide ion, pH plus POH is equal to 14, and then to find hydrogen ion, it's a 10 to the minus pH, and hydroxide 10 to the minus POH. Alrighty, so let's take a look at a problem. Now, that would be a strong acid, and when I do these initially, they're always going to be strong, so you don't have to worry about equilibrium here. It's going to go one way. Now, if you look at this, HI and H are 1 to 1, so therefore the hydrogen ion concentration is going to be the same as the concentration of the acid, so the hydrogen ion concentration is going to be 0.000267 molar. All right, now, which am I going to solve for next if I have hydrogen ion? Well, I have hydrogen ion, we want pH, so take your calculator, little thing right here, scientific calculator, negative log 0.000267. If it's a phonetic, it goes across the top. If you have one that it doesn't do that, you point 0.000267, hit log, and then hit minus. When you do that, you're going to get an answer of pH equal to 3.57. Now we only have 3 sig figs and 0.000267. You'll notice there's no units here. pH and POH don't have any units. Now how are we going to find POH? We'll go to this equation here. pH plus POH is 14, so take 14 minus 3.57, last row column. So the POH is going to be 10.47, and then we already have hydrogen ion, so the hydroxide ion is going to be 10 raised to the minus POH, 10 raised to the minus 10.47 back in the calculator again, and we're going to get a hydroxide ion concentration of 3.388 times 10 to the minus 11th. Remember, this is concentration, so we do need a unit. We need molar, and that's our answer for the first set. All right, let's look at the second one. This one is a little bit different in that although it's strong, it's binary, it's 2 here. So when we dissociate it, it's going to be 1 to 2. So taking this concentration here for the acid to find hydrogen ion, we're going to multiply it by 2. So we take 3.556 times 10 minus 4th molar times 2, you get 7.112 times 10 minus 4th molar. All right, now do the same thing, plug it in for pH, the negative log of 7.112 times 10 minus 4th in your calculator. pH is 3.148. Now we take 14 minus that value, 14 minus 3.148. We now have 10.853 because last row column. To find hydroxide ion concentration then, 10 to the minus POH, 10 to the minus 10.853. We're going to end up with 5 sig figs there. Going to be 1.4028 times 10 to the minus 11th molar. All right, one last problem. Now you try this on your own. We are doing hydroxide. So we're going to do the same thing we did with the hydrogen ion, okay, because of the relationship, it's strong, it's going to associate 100%. We're going to start with hydroxide first, and then find POH, then find pH, then find hydrogen ion, make sure the molarities for both hydroxide ion and hydrogen ion, and there's no units for pH or POH. So pause it, work through it. Ready? There's our answers. Hydroxide is 2.699 times 10 minus 4th molar, because we're going to take this number here, multiply it by 3, plug it into the equation for POH, and we get 3.569, subtract it from 14, get 10.431, then plug it in the equation for hydrogen ion, and we get 3.707. Shoot, I got the wrong sig figs. There should be one more sig in there, I'm sorry. Alrighty, either way. Okay. Now, the last thing to look at here is titration. For titration, determine the concentration of hydrochloric if... I'm going to pause this here. Okay? I made a mistake when I was recording it, so you're going to see me fixing things. It's already going to be fixed correctly on the page, so when I'm going back and forth in the video, it's already fixed. 0.0 milliliters of acid is titrated with 0.975 molar magnesium hydroxide starting in the burette at 10 members. So that's inside the burette. And then we always start with the concentration we know. We know sodium magnesium hydroxide. We have two values here. So before we do anything else, though, we have to write the equation. So hydrochloric acid, hydroic acid is binary HCl, magnesium hydroxide, MgOH. So we get MgOH twice. Double replacement or neutralization reaction. We're going to swap partners there. So magnesium is going to get with chlorine, get Cl2 and H2O. Remember, acids always give us a salt and water. Magnesium chloride is my salt and water. Balance it up. Put a 2 in front of the HCl, 2 in front of the H2O. We're good to go. Now, again, I said we start with the volume we know the concentration of, and I've got 2 here. So what I'm going to do is take the first value in the burette, or rather the last value in the burette, subtract from the first one, and we get 8.96 milliliters, and we'll put that over 1. Now we need to, in order to use molarity, we want to get into liters. So 1 liter is 1,000 milliliters. So milliliters cross out, we're in liters. We use a concentration of 0.975 moles over 1 liter. So we have 0.975 moles magnesium hydroxide over 1 liter. And again, we're only interested in 2 here. We're only interested in HCl, MgOH. The relationship is 2 to 1. So 2 moles magnesium hydroxide. Oh, shoot. That's backwards. Again, I fixed it, so you don't have to worry about it. Be 1 and should be 2. All right. And when we do that, then I'm going to have to recalculate here. Let me grab my calculator real quick, like off of my phone. All right. Oh, I hate when I do these mistakes, but we are human, and on this side of heaven, I am going to make mistakes occasionally, so I'm not going to get too uptight about it. All right. So 8.96 times 0.975, and it's going to be times 2 and divided by 1,000. I get 0.01 175. All right. So again, we'll fix that. 175. And this should be 2 to 1. All right. Now, I'll just fix it at the end of this point. We need to get, that's moles. We need to get liters. So if I have 10 milliliters, 1 liter is 1,000 milliliters. That's going to go on the bottom. And again, this is 175. And the answer there is going to be 1.75 molar. All right, fix that all up there. Good to go. Hopefully not too low. Fix that, make sure that's 1. There we go. All righty, awesome. Hopefully not too bad. Take care. God bless. Bye.